All right, we're back. Okay, if Usain Bolt ran 100 meters, 9.68, what was the speed in meters per second? Piece of cake. Meters per second. All right, you got that. Let's go backwards. What was it? Oh, in miles per hour. I think I showed that in another one, but I hate to tell you this. I threw away those notes. So remember. So for question 4, question 3, that's easy. That's just meters per second. You can do that all day long. So question 4, how do I get that in miles per hour? How do I convert meters per second into miles per hour? Well, we already found out our meters per second into miles per hour. Our factor is 0.447, and I've got to show you where we got that. We got that in the 1,609 kilometers, which is in a mile, per 3,600 seconds, or 1,600 meters, which is in a mile, divided by the 3,600 seconds. So we get meters over seconds, and that came out to be 0.447. Okay, so if we're going meters per second to miles per hour, I'm a dumbass. This is miles per hour in meters per second. Sorry about that. Now, if we're going to go the other way, since when we're going this way, we take miles per hour times 0.447 is equal to meters per second. What happens if we're given meters per second and we want to solve for miles per hour? Well, look what we have. You all know how to do this. If you've got 3x equals 6, how do you solve for x? You divide. So you divide this guy. So to get miles per hour into meters per second, you take the meters per second that you're given divided by 0.447. I better get my act together here. All right. What internal do things start to become dangerous for the human body? Okay. Did I talk about that? If I didn't, you didn't see anything. You saw nothing there. While participating in sport and an athlete becomes overheated, what steps should be taken, should the coach, or if you're out jogging in Missouri in August, take to prevent a heat casualty? Keep going, you sissy. Pain is just weakness leaving the body. Hoorah. No. Take salt tablets. Ooh, that's what they used to think. While people in desert training in the Army and Marines were dying like flies in the 40s, 50s, 60s, and 70s, and dying like flies on football practice fields in August. I think that's pretty common sense. The next few problems we're going to see, what a wonderful, okay, now this you're going to need help with. All right, so heat is removed by the body by a number of ways. Sweating, for example. If the heat were not removed, let's see how much the human body's temperature would go up, the change in temperature in centigrade or Celsius. Same thing. Okay. Heat is Q, is an energy, is equal to the specific heat of the body, which is 35. Okay, so here we go. Here's the equation for 8. All right, because this is kind of tricky. Remember this now. Q is equal to mc delta T, where Q is the heat in the body. Okay, the new heat in the body times the mass of the person times the specific heat of the body times delta T. And the specific heat of a human body, C, is equal to 3,500 joules per degree centigrade. That's not like per calorie. It's not joules per calorie. That's per degree centigrade. Okay? So there we are. Now this takes a minute. All right. So where T1 minus T2 is equal to delta T. Okay. What we're going to try and solve for is the change in temperature. Okay. We're going to see how much the temperature would rise. Okay, so T2 is the temperature after jogging and T1 is the temperature before jogging. All right. So what is mass times the specific heat? So in question 8, basically what you're asking is, if the mass is 65 and C is 3,500, what's those two multiplied? That's it, okay? I mean, I hate to tell you how to suck eggs on this thing. Now, after running for 30 minutes, the body expends 800,000 joules of energy. Okay, divide this number by your previous number. Okay, so we're going to say Q. So on question 9, just walking you through here, for some of you that are math phobic, which is fine, this class is for you, is equal to MC times T2 minus T1. So you found MC in question 8. In question 8, you found MC. We still don't know what T2 minus T1 is, but now we've got 800,000 over here. So you take what you got in question 8 and divide that. Take 800,000 divided by what you got in question 8. And that will give us this T2 minus T1 is equal to delta T. Gives us the change in temperature. Okay. How high the body was raised, which you'll see in this next slide. Your previous answer is the change in the body's temperature if it didn't regulate itself. The body pretty much regulates itself, so it tries to keep the same temperature. The average human has a temperature of 98.6 degrees Fahrenheit. We need to convert that to centigrade. So this will be the last one I do, and then I'm going to save this and move on. Okay, so then we'll go on to the next. So anyway, so the average human body has a temperature of 98.6 degrees. We've got to convert that to centigrade. And let's be careful on how we do that. All right. So this is question 10. This was question 9. So question 10, I've got 98.6. I should have just left it as 98 degrees. 0.6 Fahrenheit. Okay. Now, to get centigrade, I need to take 9/5 of 98.6 minus 32. Now, some of you that are calculator phobic are going, now wait a minute, how that? I got to multiply this? No. Here's what you do. Remember PEMDAS? Please excuse my dear Aunt Sally. Parentheses, exponents, multiplication, division, addition, and subtraction. Well, let's do the work in the parentheses first. So we take 9/5. 98.6 minus 32 gives me 66.6, right? Okay, now, to do 9/5 on your calculator, you take 9 times 66.6 and then go divided by 5. That's the way you do that. And that should give you your answer for 10. Okay? Let's make sure that's what they're asking. Okay, good. That's what they're asking. All right, so I'm going to pause here and we'll continue.